Hello viewers, in today's session we are going to discuss the function that is y is equal to f of x, which is equal to x times the greatest integer of x, right? So here we'll first draw the graph of this function by expressing this function as a piecewise function. So let us start. So here we are given the function that is y is equal to the product of x and the greatest integer of x. And we know that the domain of the greatest integer function, that is greatest integer of x, the domain is the set of all real numbers, but the range of greatest integer function is the set of integers, right? So we'll use this concept here to draw the graph of this function y is equal to x times greatest integer of x. So let us first express this function as a piecewise function. So for expressing this function as a piecewise function, what we will do, we'll take the intervals. So the first interval may be taken as x greater than or equal to 0, but it is less than 1. Right? So first we'll take this interval that is from 0 to 1, and then we'll take the interval that is x greater than or equal to 1 but less than 2, and then we can take x greater than or equal to 2 but less than 3, and so on, right? So in the positive x-axis we can frame these intervals. So this interval can also be written as interval 0 to 1. Here 0 is included, 1 is not included. And in the second interval we have 1 to 2, and in the third interval we have 2 to 3, right? And similarly we can form other intervals. For example, we can take x greater than or equal to 3 but less than 4. So this is our interval from 3 to 4, right? And similarly when we go to the negative x-axis, then we can form the interval, say x greater than or equal to -1 but less than 0, right? So this interval, so from 0 to -1. So here we have the interval that is -1 to 0. Then the second interval we can form is x greater than or equal to -1. Sorry, here we have -2, and then here we have -1, right? So this is a -2 to -1. And similarly we can frame other intervals like x greater than or equal to -3 but it is less than -2. So here we have the interval that is -3 to -2, right? So now after forming these intervals, we have to express the function y in these intervals, right? So here y is the product of x and greatest integer of x, right? So when x it lies between 0 and 1, so we'll take these intervals one by one. So when x it lies between 0 and 1 including 0, then the greatest integer of x must be equal to 0 by definition of greatest integer function. And similarly when we have the interval x greater than or equal to 1 but less than 2, then the greatest integer of x is equal to 1. So similarly we can write the other intervals here. So we have x greater than or equal to 2 and less than 3, then the greatest integer of x must be equal to 2. Similarly, when x is greater than or equal to 3 but less than 4, the greatest integer of x is equal to 3. And when x is greater than or equal to -1 but less than 0, then the greatest integer of x is -1. And when x greater than or equal to minus 2 less than minus 1, then the value of greatest integer of x is minus 2. And here x greater than or equal to minus 3 and less than minus 2, then greatest integer of x is equal to minus 3, right? So similarly, we can form other intervals, and there may be an infinite number of intervals, right? But here we'll restrict ourselves to only these intervals, and we'll utilize these intervals to plot the graph of this function. So now let us come to the function y, right? So when x belongs to this interval, then here y can be written as x times the greatest integer of x has the value 0. So here we have 0, right? So x times greatest integer of x. So when x belongs to this interval, then the greatest integer of x is 0, right? So we have x times 0, which is equal to 0, right? Similarly, when x belongs to this interval, that is 1 comma 2, then the greatest integer of x is equal to 1. So here we have x times 1, that is greatest integer of x is 1. So x times 1 is equal to x, right? And similarly, when y is x belongs to this interval, that is 2 comma 3, then the greatest integer of x is 2. So we have x times 2, so this is 2x, right? And when x belongs to this interval, then the value of y is x times 3. So here we have 3x, right? And when the value of x belongs to a minus 1 comma 0, then the value of greatest integer of x is minus 1. So we have y is equal to x times minus 1. So we have minus x, right? And similarly, here we have x times the greatest integer of x takes the value minus 2 when x belongs to this interval. So we have minus 2. So here we have minus 2x. And in this case, x belongs to the interval minus 3 comma minus 2. So the value of y is x times minus 3, because here greatest integer of x is minus 3. So here we have minus 3x. So viewers, this is the piecewise representation of this function y is equal to x times greatest integer of x, and this is the piecewise function represented in these intervals. So viewers, the piecewise representation of this function gives us the equation of lines, right? In the first case, we have the line that is y is equal to 0. That is y is equal to x times 0, which is equal to 0. So we have the line y is equal to 0 in the interval 0 comma 1. Similarly, in the second case, we have the line y is equal to x and the interval is 1 comma 2. In the third case, we have the line y is equal to 2x. The interval is 2 comma 3, and in this case we have the line y is equal to 3x. The interval is 3 comma 4, and in this case we have the line y is equal to minus x, and the interval is minus 1 comma 0. And in this case the line is y is equal to minus 2x, and the interval is minus 2 comma minus 1. And in the last case we have y is equal to minus 3x, and the interval is minus 3 comma minus 2, right? So viewers, from this we can easily conclude that all these lines are of the form y is equal to mx, right? And from coordinate geometry we know that any line which is represented in the form y is equal to mx, it passes through the origin, right? So in the first case we have y is equal to 0. So here the slope is 0, that is m is equal to 0, because y is equal to 0 represents the x-axis. And in the second case we have y is equal to x, so the slope is 1, m is equal to 1, because here if we compare these two equations, so the value of m is equal to 1, right? Okay, and similarly we can describe the other lines. Here y is equal to 2x, the slope is 2. Here y is equal to 3x, slope is 3. And in this case we have y is equal to minus x, so the slope is minus 1. Here we have minus 1. And here y is equal to minus 2x, the slope is minus 2. And in this case the slope is minus 3, right? So now let us draw the graph of this function in these intervals. So let us take the intervals one by one. So here in the first case, we have y is equal to 0, which is our x-axis, right? And the interval is from 0 to 1, including 0 but excluding 1, right? So for the exclusion of 1, we'll here draw a circle. So this is a circle, and for all values of x lying between 0 and 1, the value of y is 0, right? So the graph, it goes like this, right? So this is the graph, that is y is equal to 0, and here 0 is included, right? So this line, that is from 0 to 1, 1 is not included, 0 is included, and this line represents y is equal to 0. So now consider the second interval. So here the interval is from 1 to 2. 1 is included, 2 is excluded, right? And in this case, we have the line y is equal to x, right? So what we will do, for all values of x lying between 1 and 2, including 1, the value of y is given by x, right? So this is a straight line, and the line, it goes like this, because when x is say 1, then the value of y is 1. When x is 1.5, then y is also 1.5, and 2 is not included here. So to draw the graph of y is equal to x in this interval, we'll draw a line like this, and here we have this line. So when x is equal to 1, y is equal to 1, so we have the point 1 comma 1, which lies over here, right? And we have a line like this, right? And here I will draw a circle which shows that this 2 is not included. So this line represents y is equal to 0, and this line represents y is equal to x. So now consider the third interval. So here the interval is 2 comma 3, 2 is included but 3 is excluded. And here the value of y is equal to 2x, right? So to draw the graph of y is equal to 2x in the interval 2 comma 3, what we will do, we'll draw a line like this from 6, because when x is 3, then y is 2 times 3 6. So from here I will draw a line parallel to x-axis, and then we draw a line which is parallel to y-axis, right? So here we have these two lines. So let us take some particular values between 2 comma 3. So when x is 2, then y is 2 times 2, that is equal to 4, right? So we have the point 2 comma 4, which lies over here, right? So this is our point 2 comma 4. And for other values of x lying between 2 and 3, say for example, if we take x is equal to 2.5, then y is 2 times 2.5, that is 5, right? So we have the point 2.5 comma 5, and here we have 2.5, and 5 lies somewhere here, right? So we have the line y is equal to 2x. It goes like this, right? And here 3 is not included. So here we have a circle, and here we can have this point, that is 2 comma 4. So this is our line y is equal to 2x, right? So now similarly we can draw this line y is equal to 3x in the interval 3 comma 4, but here we are not drawing this, or we are not plotting this line. So let us straight away come to this interval, that is minus 1 comma 0, right? So when we have the values of x from minus 1 to 0, then we have y is equal to minus x. So now we have y is equal to minus x in the interval minus 1 comma 0. Here minus 1 is included. So when x is equal to minus 1, then the value of y is minus minus 1, that is plus 1, right? So the point is minus 1 comma 1, and this point minus 1 comma 1, it lies somewhere here. So we'll draw a line like this, and this is our point minus 1 comma 1. So now let us take one more point between minus 1 and 0. So let us take here x is equal to minus half. So when x is minus half, then the value of y is minus minus half. So this is plus half. So the point is minus half and half, right? And this point, it lies somewhere here, because this is half and this is also half. So the line, that is y is equal to minus x, it goes like this, right? So this is our line y is equal to minus x. And remember, this point is minus 1 comma 1, and this point is included, but here this point, that is the origin, see here 0 is not included. So here we have a circle, right? But in the interval that is from 0 to 1, this point was included, right? So this is our line y is equal to minus x. So now let us come to this interval. So here we have the line y is equal to minus 2x, and our interval is minus 2 comma minus 1. So here minus 2 is included, minus 1 is not included, right? So when we take x is equal to minus 2, then the value of y is minus 2 times minus 2, that is 4. So the point is minus 2 comma 4, right? So to plot this line in this interval, we have the point minus 2 comma 4. This is minus 2, and here we have 4, right? So what we will do, we'll draw a line like this. So here we have this line, and then we'll draw a line like this, right? So here we have this line. So now this is our point minus 2 comma 4, right? And if we take some other points or particular points between minus 2 and minus 1, let us take x is equal to minus 1.5, right? So when x is minus 1.5, which lies between minus 2 and minus 1, then the value of y is minus 2 times minus 1.5. So this is plus 3, right? So here we have minus 1.5, and we have here 3, right? So we have this point, that is minus 1.5 comma 3. It lies somewhere here, right? And now when x is minus 1, although this minus 1 is not included, so when x is minus 1, then y is minus 2 times minus 1, that is plus 2. So we have minus 1 comma 2, right? So we have here minus 1 and here we have 2. So here we have this point, right? So this point is not included. So here we draw a circle. So our line y is equal to minus 2x in this interval, it may be plotted like this, right? So this is our line. Y is equal to minus 2x. So similarly, we can plot this line y is equal to minus 3x in this interval, and this is how we can plot the graph of this function y is equal to x times the greatest integer of x. So this is the graph of the function y is equal to x multiplied with greatest integer of x. So let us now examine the continuity of this function at x is equal to 0, right? So let us first find the right hand limit. So the right hand limit is given by limit x tends to 0, and here we have the positive sign, and here we have the function f of x. So we'll take x is equal to 0 plus h. That is the point x is equal to 0 plus h is in the vicinity or in the neighborhood of x is equal to 0. And it lies towards the right of x is equal to 0. And here h is infinitesimally very small, and h is a positive quantity, right? And h, it lies between 0 and 1. So the right hand limit is now given by this limit, and we are taking x is equal to 0 plus h, that is h, and when x tends to 0, then h tends to 0. So now we have right hand limit h tends to 0, and we have f of 0 plus h. So this is the limit h tends to 0, f of h. Now we can write f of h from this expression. So replacing x by h, we have h, then here we have greatest integer of h, right? Now see, here we have greatest integer of h, and h lies between 0 and 1. So the greatest integer of h must be equal to 0. So now we have limit h tends to 0, h times 0, so that is equal to 0. So the right hand limit of this function at x is equal to 0 is 0. Now let us find the left hand limit of this function at x is equal to 0. So the left hand limit is given by limit, and here we have x tends to 0 minus, and here we have f of x, right? So now we'll take x is equal to 0 minus h, and this point 0 minus h is in the neighborhood of x is equal to 0, but it lies towards the left of x is equal to 0, right? So when x tends to 0, then h tends to 0. So we have x is equal to 0 minus h, that is minus h, right? So now we have limit h tends to 0, and we have f of minus h. So f of minus h can be obtained by replacing x by minus h. So we have minus h, and then we have greatest integer of minus h. So now the greatest integer of minus h is equal to minus 1, because when h lies between 0 and 1, then minus h lies between minus 1 and 0. So the greatest integer of minus h should be equal to minus 1. So now the left hand limit is limit h tends to 0, and here we have minus h, and here for greatest integer of minus h we have minus 1. So this is limit h tends to 0, and minus h multiplied with minus 1, it is plus h, and this limit is equal to 0, right? So we see that the right hand limit and the left hand limit both are equal to 0, and they are finite and they exist, right? And moreover, the value of the function, that is y is equal to f of x at x is equal to 0, is given by f of 0, which is 0 times greatest integer of 0. So the greatest integer of 0 is 0, so we have simply 0, right? So we can see that the right hand limit is equal to the left hand limit is equal to the value of the function at x is equal to 0, and all these three quantities are equal to 0. So by the definition of continuity of a function at a given point, we can claim that this function is continuous at x is equal to 0, and which is quite evident from the graph, because here there is no gap, right? So the function y is continuous at this point, that is at x is equal to 0. So viewers, this is how we can examine the continuity of this function at different points. We have just seen that at x is equal to 0, the function is continuous. But at these points, that is at x is equal to 1, and then x is equal to 2, and here we have x is equal to minus 1, and x is equal to minus 2, and so on. At all these points, the function is discontinuous, because see, at these points, the graph of the function is not a smooth curve, right? And here we have a jump. For example, at x is equal to 1, similarly at x is equal to minus 1, we have a jump here. Similarly, at x is equal to 2, we have a jump here, and so on, right? And we can also prove the continuity, discontinuity of this function at these points by the method which we have just shown. Similarly, we can check or examine the differentiability of this function at the given points. And from this given problem, we can also prove that continuity is not a sufficient condition for the differentiability, meaning thereby that all continuous functions are not necessarily differentiable, right?